miles below the ocean surface. Where sunlight never reaches and pressure can crush steel, machines are working nonstop. They map the seafloor, repair global infrastructure, extract resources, and observe life forms humans may never see directly. Almost everything we know about the deep ocean comes from technology built to survive one of the most hostile environments on Earth. Deep sea technology. Deep sea technology refers to the systems and machines designed to operate at depths typically beyond 1,000 meters, where hydrostatic pressure exceeds 100 atmospheres, temperatures are near freezing, and communication with the surface is severely limited. These technologies enable exploration, monitoring, construction, and maintenance in the abyssal and hadal zones of the ocean. The primary challenges shaping deep-sea engineering are pressure resistance, corrosion control, energy supply, navigation without GPS, and data transmission through water. Because radio waves attenuate rapidly in seawater, most deep-sea systems rely on acoustic communication, fiber optic tethers, or autonomous operation with delayed data recovery. Pressure, environment, and structural design. At a depth of 4,000 meters, ambient pressure reaches approximately 40 megapascals, equivalent to placing the weight of several fully loaded trucks on every square centimeter of exposed surface. To survive this environment, DC systems use pressure-tolerant designs rather than attempting to resist pressure entirely. Pressure housings are commonly spherical or cylindrical with thick walls made from titanium alloys, high-strength steel, or syntactic foam composites. Spherical geometry distributes stress evenly, reducing material fatigue and minimizing weak points. Electronics are either enclosed within these pressure vessels or immersed directly in pressure-balanced, oil-filled compartments to eliminate differential pressure across components. Seals and penetrators are critical failure points. Electrical and optical connections passing through pressure boundaries use glass-to-metal seals or ceramic feed-throughs to maintain integrity over long deployments. Remotely operated vehicles. Remotely operated vehicles, or ROVs, are tethered underwater robots controlled in real time from a surface vessel. The tether contains power conductors and fiber optic cables for high-bandwidth data transmission, allowing operators to receive live video and sensor data while sending control commands. ROVs are typically equipped with multiple thrusters for precise maneuvering, robotic manipulators for physical interaction, and payloads that may include cameras, sonar, sampling tools, and cutting equipment. Heavy work-class ROVs are capable of lifting hundreds of kilograms and are widely used in subsea construction, pipeline inspection, and cable repair. Because the tether adds drag and limits range, ROV operations require dynamic positioning systems on the surface vessel to maintain station over the worksite, compensating for wind, waves, and currents. Autonomous underwater vehicles, or AUVs, operate without tethers and follow pre-programmed missions. They rely on onboard batteries, inertial navigation systems, Doppler velocity logs, and acoustic positioning references to determine their location underwater. AUVs are optimized for large area surveys and data collection rather than physical manipulation. Common missions include bathymetric mapping, seabed imaging, magnetic surveys, and environmental monitoring. Their streamlined shapes reduce hydrodynamic drag, allowing them to cover hundreds of kilometers in a single deployment. Because communication bandwidth underwater is limited, AUVs store most data internally and transmit only status updates acoustically. Full datasets are recovered after the vehicle returns to the surface or docks with an underwater station. Human-occupied vehicles, also known as deep submergence vehicles, carry pilots and observers inside a pressure-resistant hull. These systems provide direct human presence at depth, offering intuitive visual assessment and manual control that is difficult to replicate. Remotely, the pressure hull is usually a titanium sphere with small acrylic viewports designed to withstand extreme compression while maintaining optical clarity. Life support systems regulate oxygen levels, carbon dioxide removal, humidity, and temperature from missions lasting several hours due to high cost, operational risk, and limited endurance. Human-occupied vehicles are used selectively, often for scientific observation, archaeological exploration, or specialized inspection tasks where real-time human judgment is critical, sonar and seafloor. Mapping systems, because light penetration is negligible in the deep ocean. Acoustic sensing is the primary method for perception and navigation. Multi-beam echo sounders emit fan-shaped acoustic pulses and measure return times to generate high-resolution maps of the seafloor. Side scan. Sonar systems provide detailed imagery of seabed texture by measuring the intensity of sound reflected from different surfaces. These systems are towed behind ships or mounted on UVs and ROVs to detect objects such as wrecks, cables, and geological features. Sub-bottom profilers use lower-frequency acoustic waves to penetrate sediment layers, revealing buried structures and stratigraphy beneath the seafloor. Power and energy systems. Deep-sea vehicles rely on electrical power delivered either through tethers or onboard energy storage. ROVs receive continuous power from the surface, enabling high-performance operation without endurance limits. AUVs depend on rechargeable batteries, typically lithium-ion or silver-zinc, chosen for high energy density and reliability. For long-term installations such as seabed observatories, power may be supplied via subsea cables or generated locally using seafloor batteries and energy harvesting systems. Thermal gradients, ocean currents, and microbial fuel cells are areas of ongoing research for extending deployment durations. Power management systems are designed to prioritize critical functions and protect batteries from pressure-induced deformation and temperature extremes. Materials and corrosion control. Seawater is highly corrosive, particularly under high pressure and in oxygen-rich environments. Deep-sea systems use corrosion-resistant alloys, protective coatings, and cathodic protection to extend operational life. Titanium is favored for pressure housings due to its strength-to-weight ratio and resistance to corrosion. DSPIT high material and machining costs. Syntactic foam, made from hollow glass microspheres embedded in resin, provides buoyancy while withstanding immense pressure without collapsing. Biofouling is less severe in deep water than in shallow zones, but microbial corrosion and mineral deposition still influence long-term design considerations, applications, and operational scope. Scientific exploration uses deep-sea technology to study tectonics, hydrothermal vents, deep ocean ecosystems, and climate records preserved in sediment cores. Industrial applications include offshore energy production, seabed mining research, and maintenance of global communication infrastructure. Military and security operations use deep-sea systems for surveillance, object recovery, and infrastructure monitoring. Environmental monitoring networks deploy sensors on the seabed to track seismic activity, temperature changes, and chemical composition over long time scales. As ocean activity increases, deep-sea technology plays a growing role in understanding, protecting, and exploiting the largest environment on Earth.